Okay? So I want to make sure that everybody understand. This course will be given in English, not Chinese. So you can change your mind now and get out of the room. Because I was forced by the school to give the English course. This course was given in Chinese last year, and suddenly the university notified me that the number of English courses is not enough. So but they decided to split the VLSI design into two parts. Chinese course will be given by Professor T.J. Lee, who was my student before. And this course will be totally given in English. So you can change your mind, and there is a door. Okay, you can walk out there, nobody gets hurt. Is that understood? So you're fine with sitting here, listening to my English? Is that right? Okay, then be my guest. Okay, and we'll start recording. Okay, these are two TAs. One is from Philippines. Okay, raise your hand, Mr. Ralph. And the other one is from Taiwan. Okay, they will give the, the lecture in the night to teach you how to use those tools that we are supposed to use in this course. And the course, the main goal of this course is to help students who are really interested in IC design to tape out an educational chip through the help of TSRI. And it'll be very tough for those students who never had experience in IC design. You're the beginners. Well, don't be intimidated by me. If you have a real big heart, and you will learn a lot, okay, after this course. So you can consider this as a first stepstone if you want to get into the juicy semiconductor business. This is what I want to say. So we are going to give the lecture only maybe 80 minutes to 90 minutes, because today really is a really bad day for me to give the course. I just joke with my TAs. Today is a Super Bowl day. And right now, I just watched a half a game, and I'm going to miss the second half. This is really bad for me. All right, have your seat. So we're going to start our journey. All right, okay, so you boys want to sit here, or you can get out. You can come back about 10:20 or 10:30. All right, have your seat. And there will be no hardcore stuff today. Today is only the introduction of this course and what is going on in the semiconductor in Taiwan and the world. So my name is Chao Ching Wang, and I'll give you some of my background. First thing first, I'm really old, okay? I got my PhD before you were born. Okay, I got my PhD in last century, 1992. Okay, I'm older than most of your parents, okay? Right now, I have been teaching this course for over 3 decades, 30 years. I got my degree in Taiwan NTU, WE, 1984. That is the year, okay, I graduated from the college with Michael Jordan, the same year. So Michael Jordan right now retired already. I'm still standing here to give the course. Okay, I have been the chairman of this department, dean of the College of Engineering. Right now, I'm the vice president of office and research development of this school. Okay, I published a few papers. Okay, well, if you're old enough like me, perhaps you publish more. I have over 170 patents, okay, including like 40s in USA and 20s in China, okay, and I have some technology transfer. This is just some of the honors I've earned in my past a few years. Okay, last year I was invited as a joint honor professor by university in India. Okay, so today I'm going to give you some background or introduction to semiconductor. More specifically, it will be about the IC design, okay, because this course is the first course for IC design. And what IC is, and what IC can do. Okay, that's one thing that most students would like to know. Well, before we go to the details, let me tell you one thing. because raise your hand if you are double E background. You are double E, electrical engineering here. Your major is electric. Raise your hand. Don't be shy. All right. Okay. Good. So you are lucky. You are lucky guys and lucky girls. Well, I'll tell you why. Because a double E department, the major function of double E department is to train students into engineers, and there are three types of engineers. Okay. The first type is those engineers who fabricate ICs, integrated circuits. Okay, the semiconductors, a lot of process technology things. And the second type of engineers is the engineer who design the ICs. Okay, the first one is a fabricate, the second one is design. And number three, which are the major or the majority of students in Department of EE, is those engineers who use ICs, okay, to solve a lot of our problems. For example, communications, control systems, motor control, okay, automobile, this kind of thing. So the engineers, okay, fabricate it, design, and use ICs are three major types that EE department would like to train. So in this course, we teach the students how to design the ICs, all right? So the background of this course is that what IC industry was and what it is now, and then what the IC design or IC industry will be in the next decade or next 30 years, okay, after I retire. And why I say that IC design is very promising, I'll give you some numbers because students like numbers. Okay, everybody believe in numbers, even though sometimes numbers will be distorted. Or sometimes it will be misleading. Okay, and I'll tell you some of the basic IC design flow. Well, unfortunately, okay, I will not be as familiar with as my TAs because they are students, graduate students in my lab. They play around with these tools all day long, but I have not played with these tools all day long. So most of the time, when you run into a problem, it's better for you to consult with them, not me, because they are the players, okay? I'm just a coach. Okay, and the last one is, if you want to stay in this course and you have a determination, okay, so stay with us for the entire semesters, I'm going to tell you what the requirements of this course is. Okay. Well, this is a very typical picture to show what the IC is. On the top, upper right-hand side on the top, you will see that a small black dot on the fingertip. That is what the IC is, if you look at, without the help of any electrical or microscope. Okay, that is very tiny small. Okay, but this small thing drives our human civilization very rapidly, all right? And these are just some examples that are designed by my students before. Okay, when you use a microscope, you look into it, this is how it looks like, very differently, okay? This way, this is the old-fashioned one. This is probably the oldest one that my lab has ever taped out. Okay, it's very, very old. And then there's a cell base, and this is the one I cannot remember. I think this is a 0.6, this is a 0.35, and this is 0.18, I think. I cannot remember exactly. Anyway, it shows the footsteps that the students before you ever tape out to design their chip and make it in real. Okay, this is called die. This thing is called die. So sometimes I was joking about it. It could be die for it, okay? And then after you tape out the chip, okay, you are going to get help from TSI or other service company because it's impossible to measure directly, and that's a little thing, okay? If you ever really did all the EE laboratories, okay, in your sophomore year or the first year of your college, okay, all the instrument you use in the lab, in laboratories of a department is very big. You cannot directly use the the probe to probe that thing. That's impossible. So you got to have something to probe in. This is called the packaging. And then you see a lot of metal legs we call pins, okay, with the correct terms. It's called the pin, terminal pins. Then you, then you solder the pins on PCB board. Then you can use those expensive instruments to measure the performance or the function of this chip. So this is a chip sitting in the middle of this plastic box, okay, and a lot of traces, which could be alumina or copper, and then you have a lot of pins. The pins can be directly measured, or you can solder them on the board, and then you can use a lot of instruments to measure it, and then see the waveforms, to see the spectrum analyzer, something like this. So this is the this is how it's going to work. Okay, and this is called a monosolic ICs in the plastic packaging. Basically, this is what you're going to get. Okay, if you finish this course and tape out your chip, then about 3 months later, maybe 4 months later after this course, you get that thing back. Then you will do the measurement. And then you can use the achievement that you have done in this course to show that how good your chip is in your interview with some companies in the future. Okay, this is just a typical example. Okay, developed by my student before. See that? This is the chip designed and taped out by my students before. Okay, and soldered on a PCB board. This is a very lousy one, low-end one. Okay, and we use a lot of auxiliary circuits to do the testing. In the meantime, we got to use a scope to see the waveform. Of course, we need a power supply and a function generator, okay, to do that experiment. So in this course, we teach only how to design it. But after that, okay, one of the guys in the team that you assemble, okay, will be in charge of the measurement here. It is my advice. Okay, if you want to be a real IC design engineer, okay, it's better for you to have the hand-on experience to do the measurement. You will gain a lot from this kind of thing, okay? You're running into a lot of troubles. Damn, you got to ask yourself, okay, damn, how the hell my chip why does it work? Okay, and the power supply you'll find out is very dirty, okay? And you will see a lot of noises on the scope. I assume that the word is perfect, that there is there will be no noise, but the reality is not, okay? The reality is not. You will understand that you will see a lot of noise coming from the power supply, and the power supply is hooked on the outlet on the wall that you use. You understand how dirty, okay, in terms of the noise, how dirty the power is. This is a function generator. All right, so this is just an example to show you how to do the measurement if you do have the chip back. Oops. Okay, so let's assume that you become an IC designer. Then single IC will not be considered as a real product. If you don't believe me, you can ask your parents, okay, whether they want to spend a few dollars to buy an IC and go home. They can do nothing about it. Right? You can go home and ask your grandma, okay, what the IC is. Trust me, they don't understand what the hell is. But the IC is just like the building blocks of a system. You need a lot of ICs, okay, and with the software, we call that driver. And then we solder them together and use a microcontroller to drive these ICs. So on a meaningful product, for example, your phone, your laptop, okay, I bet there are hundreds, maybe thousands of ICs. For example, in the EV car, Tesla, for example, Tesla. Whoever has a Tesla, please raise your hand. Oh, come on, okay? Okay, even a scooter. Tesla, I can give you some numbers. A fuel car, okay, very typical fuel car. At least 2,000 chips are installed in the fuel car. Like a Toyota that you drive, okay, 20. For the EV car, Tesla is an example, 6,000 chips, okay, in that car. So Okay, there are different kinds of ICs over here. There's digital IC, analog IC, a lot of coppers over here. And this is so-called the passive elements. Passive elements stand for three things, basically. Resistors, you understand? Okay, coil, that's inductors, and capacitors. Okay, basically, we have three types of passive elements. All right, then what a system is. This is a system. After assemble all the chips on the board, then you put on the LCD display with a very nice looking outfit and the case, then it becomes something that you like. For example, the phone. Everybody has a phone, right? Right now, but perhaps you have 2 phones, maybe 5 phones, okay? I remember one of my lady graduate student before who was very pretty. And the interesting is someday she called me with a number that I don't understand. I don't remember. I said then the day after the call, I met her in the lab. I asked her, what the phone number is, why you had used a different phone? She said, sir, I have 5 phones from 5 boyfriends. So that's we call that the parallel processing, okay? So that that way she will mess up with the numbers and the girls she has a 1-to-1 mapping mathematically. So 5 phones from 5 boyfriends. That's a good thing. So that's why the iPhone sale curve goes up all the way down, all the way up. So this is a very typical example. All right, and it is my understanding that everybody understands this thing is called the Moore's Law. Moore's Law was predicted in 1960-something by Gordon Moore. Well, about a half century ago, this gentleman said that, okay, in the future to come, okay, the number of devices on a single area will be doubled in every 2 years. That's what he said 50 years ago. And that's a very bold prediction. Okay, he said that 50 years ago, 1960s. And the funny thing is that what he said was exactly match. Well, what he said was exactly match what we happened after that. See that? This is a number of this is the line for the processors. Okay, there are 2 big things, 2 gigantic ICs in the system. The first one is a microprocessor, okay, which was dominated by Intel about 20 or 30 years ago. Lately, Intel was knocked out from the crown. Right now, AMD and ARM right now is a leading group. The other one is the size of DRAMs. DRAMs is a main memory of your microprocessor, or is your computer or a laptop. So basically, this is a log scale. So this is a linear. This is a line, linear line. So basically, this matches whatever Mr. Gordon predicted in 1960s. And well, something is slightly changed. Okay, what he said was every 24 months, 2 years, the number will be doubled. But the thing is, after that, it be somewhere around this 18 months, even faster than what he expected. But it's very scary, okay? It's very scary. This is a very famous one. And thanks, why that we have this kind of fascinating development of the ICs? It is because the advance of the technology, the size of the device, okay, has shrunk, okay, by half every 24 to 18 months, okay, the device size. So you heard a lot of terms from the news reports. For example, 7 nanometers, 5 nanometers, or 3 or 1, this kind of thing. And you were bombarded with those messages from the news report that TSMC right now is a world-leading fabrication foundries in the world. Yes, it is. Okay. Why? Because TSMC spent a lot of resources, including human and the money, to push the technology forward. And the best, okay, the most important part of that one is the shrinkage of the size of the device, which is the width of the transistors. This is very stunning, very astounding. Okay, this graph is kind of old, it's over 2020, but this is all the way down. The only problem left is that whether we have a limitation of this line. Yes, we do. Because the limitation is that, okay, no matter how hard we try, okay, at least you need one single atom for that transistor. So that will be the limitation of physical Moore's law. All right, okay? So we don't know what happened after that because I don't give a damn. I'll be retired. But you boys and girls will be serious concerned whether there is a limitation about that. Okay, and what are the categories of IC products? So basically, we can, I'll give you some, understanding of what is the world in chip and what is the world in reality. Okay, the reality in the world is given by the nature, Mother Nature. Everything is analog. For example, you hear what I'm saying. This is acoustic wave is analog. Okay, the wave you see, okay, on the seashore is analog. Everything in nature is analog. But, however, okay, human civilization is fully digitized. Because the digital signal, okay, can be restored, okay, can be reduplicated, okay, can be faithfully broadcasted using the internet. So the world that we built is civilized, is a digital world, okay, which is slightly different from the Mother Nature. Okay, the second thing is that ICs everywhere in our life. Okay, as soon as you open your eyes in the morning, okay, you are using the cell phone to wake you up. It's a known. And then you see the projector and the contents I'm showing you it's also by the ICs. So this thing penetrates very deeply in our life. Okay, but the thing is that the lifetime of IC product is very versatile. Okay, different ICs, their lifespan is quite different. Okay, for example, the cell phone, I think most of the students will use it like in 3 to 5 years. That's it. But for those ICs in your power plant, they're expected to operate at least 10 years or maybe 20 years. Okay, and for those ICs used in the satellite or in the space shuttle, okay, they expect that this thing could run up to over 30 years. So different lifespan require different reliability. So it's so versatile. Okay, and right now there are 5 major end product usage: mobile phone, okay, cloud data center, everybody use it. It is my belief that you use a lot of cloud storage, cars, okay, and military and aerospace. All right, and the medical. Everybody gets sick. Okay, these are 5. I personally believe will be the major IC application area. So if we go down to the features of the ICs, you can classify them into these categories. Or I showed the pie share in 2017, but it's almost the same. I forgot to update it. So basically memory, the big one, and logic, which stands for a lot of the AND OR gates. So these are small, teeny, tiny ones, the microprocessors. And the number 3 is a micro components, integrated circuits, including sensors. And analog. Analog is very important. because we need some ICs to do the translation between the digital world and the real world. So we needed analog ICs, okay? And as I say, okay, in my previous slides, so in the future, Power IC and the AI, right now it's very hot. You can ChatGPT, this will be the next two booming markets. Okay, I'm saying really booming, really prosperous. Okay, Power ICs, because energy or the natural resources so limited. So you gotta have power ICs to do the power management, or so-called the energy management. Okay, we like to save a lot of power as much as we can. And then AI, the imagination of AI is way too much. Okay, it is our belief that AI is going to kill or eliminate a lot of jobs in the future. Okay, for those jobs who needs recognition and boring computation, okay, AI can help us to do the reduction of complexity. So in the future, that for example, face recognition is very reliable. So the security job, the security will no longer need it. Okay, we don't need a security guard. All we need is a lot of cameras and very reliable AI recognition systems, and we don't need a security job. So all the security guards will be out of the job. Okay, very soon. This is just one example, and accountants as well. Okay, this is a growth rate. Top 10 is 2021, about 2 years ago, so it's very, very new. So these are the top 10, okay, growth rate ranked by the sales. See that? The first one is that special purpose logic, microprocessor. Number 2, memory, DRAM. Then see that? Auto means a car, consumer. The cellular phone, auto, okay, display. Okay, wireless, and consumer. So you see that the main growth rate, the excuse me, the main product, that's 2 years, you see that microprocessor, memory, power, okay, and cellular phone. Right, so this is the some stats that students like to know. So since I emphasize how important the power is, I'll give you some examples. This is just for those ICs in the car, okay? Because the battery voltage of a car is about 24. Okay, it's not 5, it's not 3. So you need to bring down the power supply voltage so that other components can use that power supply. So you need a lot of converters, okay, down conversion. So this is a battery, okay, so need an adapter. This is what you see in the car. And this is 24 to 48, okay, power supply, AC lines. And these are the end products, mobile phone, USB, sensors, okay, so on and so forth. A speaker, you like to hear music, stereo in your car, for example. And you gotta have a panel in front of you so that you can see the GPS and the tour guide, for example. And lighting, of course, in the car is also critical. So this is for the power ICs. And for the AIs, okay, I cannot find the English one, so I use the Chinese ones for you to understand. That is just a figure to do the illustration for you to understand. So in the future, that we expect the chip can be used to replace the brain. Okay, so you gotta be careful. Okay, your brain might be replaced with some chips in the future if you don't use it. Okay. But right now there is still a big problem for the AI chips. I will talk about that later. All right. So we have a cloud AI, we have edge AI, we have a terminal device AI, this kind of thing. So what is the ultimate problem for the AI is a power. It is a power. Power is a problem, okay? We'll talk about that later. And this is a video that we took about 7 years ago. about 7 years ago, 10 years ago, we predict that this is what will happen. And some of them already exist. Okay, this is called environmental factor savings. Right now, it's very popular everywhere. You get up, all less people there. Okay, you start. There are some sensors to tell you what is your heart beat rate, what is the temperature right now. Okay, and this already are in the market. Right now we have this kind of things that okay, the camera everywhere. We get a lot of scooter drivers that have the helmet to record what happens, and this is the EV car. It's already there. This is one of the national program are involved. Why Taiwan matters? Why Taiwan is so important? Why the redneck Americans come to help? Because Taiwan right now play a critical position in the world supply chain, ICs. Taiwan is the only country in the world, okay, which has a vertical full supply chain, okay, from the top, the IC design idea to the bottom, okay, that is packaging and testing. So right now we are the number one in foundry service, about 70%. So I will always joke with my foreign students that every 2 out of 3 chips are made in Taiwan. It's a fact. It's a fact. Right now, China is beaten so badly by Americans because Americans are tighten up the neck of Chinese. And a lot of companies right now moves to Southeast Asia and India. Right now, Indians are so happy, okay? They like to take everything from China, and they don't like each other for a century. Right now, they have a very fat chance to kick the China out of their playground. And number one is in the world that Taiwan has. And number 2 in IC design, next to American. American has like a 60% because they have Qualcomm, okay? They have Broadcom, all right? And they have ARM, this kind of big name company. Number 2 in DRAM, okay? Number 1 is Korean, which I hate most, okay? Wow. Well, I know you boys and girls like a lot of girl dancer group in Korea, but okay, as an IT designer, okay, this is the guy we have to beat in the future. Korean have 60% of the DRAM market share. Taiwan only has 20. Okay, we are way behind, and we are number 1 in packaging and testing. Okay, we are part of it, and the best part of this is that the number 1 company in testing packaging is only half hour from this school. It's in Nan's scientific car is called ASE. In Chinese, it's Ruyue Guang, okay, which is students hate a lot because they pay very low, okay. All right, and then a lot of uh, companies have been developed thanks to the success of IC design, including information tech, communication tech, and automobile. All right, and this is a very new things for you to understand. The development of Taiwanese semiconductor industry, see that? This is IC design in blue chart. In the blue bar, manufacturing is in yellow, and light blue is memory, and I see OSAT is a testing. So we can see the distribution of this segment. And you'll see that the yellow bar grows higher and higher. That's because the success of TSMC. And the next one is UMC, right? So this is the, in 2022, okay, Taiwan semiconductor production value hit, okay, NT 4.7 trillion. Okay, I don't know how many zeros are. You can go home and do it, okay? And the increase rate is over 15% compared to the global growth rate about 4. So it's very scary. we are standing on the top of the world. That's why the redneck Americans, excuse me, okay, they are recording it, okay. It's better for me not to curse a lot. They send their troops to protect Taiwan. Okay, and this is why I say that Taiwan has a vertical full supply chain. See that? We have a mask manufacturing, wafer testing, packaging, testing, design, and system manufacturing, distributions. We have everything, okay? Right now, the IC design houses, the number of IC design houses over 300, okay? And we have a couple of number of foundries so these, these are the number of companies. Design houses is at 238. And this is wafer manager 13, okay? So it's a very healthy environment for those students to grow with them. So right now, I'll give you some numbers to, right now, this is the real numbers. We are number 2 in IC design in the world. Okay, number 1 in the foundry, over 60. And packaging and testing is all over 60. See that? You should feel proud of that, okay? And hopefully in the future, you'll be part of the team. Because I'll retire, and the future is yours. And this is just some symbols of brand name companies. So we don't have time to go through every one of them. Okay, this is a full supply chain in an island. So we call that upstream. Upstream means that you need a lot of effort in your mind, okay, instead of capital. So the added value is higher. So the foundry and the design, we need a lot of brain power, okay? And for the downstream packaging testing, we need a lot of capital. We need land, okay? We need big factories and the plants. So it's capital intensive. And the profit margin, this one is higher than this one, all right? So that's why the salary, okay, of the employee in the upstream company is much higher than that salary in those companies in this part. That's why a lot of students complain that ASE and other brand name testing companies, they pay relatively low. Yes, because the profit margin here is lower than those on the top, okay? So that's a natural thing. Okay, this is how the IT design flow is. And we are we are here, okay, design engineer. So your job, in case you really want to be one of the IT designer, you are going to sit in front of the computer and use a lot of expensive software to do the design. Then you are going to talk to your boss or discuss with your teammates, work together. Because besides the college, all right, all the IC design project in a company is not developed by one single person. No way, because they would be very complicated. So that a lot of companies ask me, the student got to have the ethic or the concept to be a team player. okay, you won't work alone. You want to work alone, fine. Go to be a YouTuber, right? You can work alone. But in IC design, reality is that you have to work with a lot of guys. For example, the Pentium 4 IC processor, the microprocessor, okay, the whole team is assembled by 150 engineers. 150. Okay, so you got to work with others. So the communication skill is important. So English is important. Okay, and then you send your design to the foundries and then tape out, then you got your product. Okay, this is IC design, the very simple flow. Okay, so if you want to find a job, okay, this is how the job is, okay. IC design houses is on the top. So this is basically what we're going to talk in this course. Okay, from the gate level, flip-flops, layouts, and the verification. Then, after the verification is totally done, we send out the design file, GDS2, to the foundry, which could be UMC in this course. I will ask you to use the UMC because UMC is more friendlier than the TSMC. I'll tell you why later, all right? And you don't have to pay. And then after the verification, we send the die to the ASE, this kind of company, to the chip testing. Then you have a lot of chips. Then you assemble them on the board. And then send it to the brand name company, for example, the Apple, okay, the Asus, okay, and then go to the distributor to be sold, and then the customer will come to the shop or using the online shops to buy your products. This is the entire, I would say this is called the value chain. Okay, so this is the numbers. Okay, we are number 1 in foundry, number 2 in IC design, and the overall, okay, production value, we are number 2 in the world. Surprise! This is a very teeny tiny island, and every one of my foreign friends, they were so surprised. How the hell you do that? Okay, based on these numbers, the foundry service, okay, has the highest growth rate, averagely, in the past 20 years, 88.5. And memory goes down because Korean is pushing really hard. So that's why I say that the next battlefield for us is that we have to take the number 1 position back in the memory area. Right now, Samsung and Hynix, okay, they are top 2 companies in memory design and fabrications. This is the pie chart of Taiwan right now. Okay, foundry has like 50%. IT design has a quarter. Okay, and the rest has another quarter. So right now, if you take the course and you want to transform yourself into IT design, you probably will work here, and some of them will work here. TSMC company also hire IT designers. They have their division to help their customers. All right, I have a lot of students in these companies, and these are the top 10 companies in Taiwan. Well, these are the monsters. Okay, these 10 companies occupy 3/4 of the entire market share in Taiwan. Number 1, TSMC. Number 2, MTK. And then UMC number 3. And 4, 5, 6, they are all testing and packaging, okay, the ASE. And number 7, this is a memory company. This is Power Chip, okay, foundry. And Novatech IC design again. Number 10, memory. So basically, foundry service, design, and memory. Okay, top 10 companies. All right, we're going to skip this part. As I said, in the future, that 5 categories. But however, the military and aerospace is so hard for the usual or average company to achieve. But these 3 parts are the future battlefield for a lot of IC design houses, medical, electronics. Okay, green means power. Okay, power and energy related electronics. And 4 C's are the traditional 3 C's plus car. There's 4 C's ICs. So military and aerospace is a very interesting domain. Unless you have a very strong connections, it's impossible for IC design house to have a deal with the defense department. It's impossible. Or what's it about? How the hell you can sell the chips into a submarine? Think about it. Unless you have a very strong connection, okay, with those big guys in the government. So how the hell you can sell the chips of a tank? It's impossible. All right? So the feature of IC design industry is that rule number 1, winner takes all. Because it's pretty easy. For example, if your beloved ones, like your parents or your grandma, or in the future your wife or your husband gets sick, then the doctor told you that, okay, I have medicine number 1 and medicine number 2. Medicine number 1 comes from American. A single pill costs you $20,000. And number 2 is made in Taiwan, $20. Which one you want to take? 99% of you will sell your house to buy the pills or the medicines from America, right? Because it is your belief that you have a better chance to cure your beloved ones. It's the same thing in semiconductor here. If I have enough money, of course, I will ask the number 1 company to tape out the chip for me, which is TSMC. You know what I'm saying? Okay, unless this product is so-called the cost-effective product or the commodity. Otherwise, if I have enough money, I always go to the number 1. That is why I say the winner takes all. All right, and the profit margin is so different for different different products. For example, the power ICs and CPUs. The profit margin of CPU could be as high as 70%, but the power ICs is so small and so cheap. A lot of companies can do that at 7%. So it's very diversified. The range is so dynamic. Number 3 is that, okay, if you want a company wants to grow bigger and stronger, the partnership, how close you are with the foundries is important. All right? Because the time to market is a major factor. Okay, 2 companies who can deliver and design the same product, but the number 1 company that they have a strong connection with the TSMC, maybe they share the stock with the TSMC, they got the time shorter to deliver their product, and the numbers must wait for another year. Who is going to survive in the market? Of course, the number 1. Number 4, now this is related to you, because we need a lot of talents, engineers, with intensive domain knowledge. And IC design needs a lot of domain knowledge. That is why you got trained in the school, you got educated here. All right, you got to learn how to design it and what are the rules is. Okay, now talk about jobs. This is what the students care most. Okay, these are the stats from the Hsinchu Scientific Park. You see the numbers over there? The number of employees grows all the way up, no matter the economy is bad or good. Okay, and the number of companies, okay, is all the way up as well in the past 20 years. So if you stay in this area, I'll tell you, you come to the right place. I cannot guarantee you'll become a millionaire, but I give you a chance to change your life. This is what I told. This is what I told to all my graduate students. Okay, Taiwan's most hot, okay, position. 3 types: insurance, sales. You don't want to be that, right? Okay. Number 2, RD. Number 4, semiconductor. Semiconductor and RD. Okay, this is a number that you care most. What is the salary you get? Okay, read numbers. This is from the 104 104 website. This is analog ID designer. The average salary per month, 85K. And digital ID designer, 83. And the range could be as high as over 100K. And this was about 2 years ago. Right now it's even higher. So I told my students, if you can survive, you won't regret to get this job. But however, nothing comes free. Because in IT design house, okay, it's very competitive. So basically, it's 9 to 9, according to what my students say. Okay, you work from the 9 o'clock in the morning, and you most of the cases you will stay in the company up to 9 in the evening. Right? And if you go, if you are hired by MTK, which is the number one in the Taiwan IT design housing right now, according to what my students say, the average annual pay will be 1.5 million to 2 million for the entry-level engineer. You cannot find anything better than this. No, you can't. Unless you are born with a silver spoon, or your father have a train store for you. So the design flow is quite easy. Okay, basically the entry these tools, there are two ways to do that design. The first one is called the coding, which we will not cover in this course. We don't have that kind of time. And in this course, we are going to teach how to use the SPICE and the Virtuoso tool. That is entry level, use a manual way to design. Okay, you have to draw all the transistors and all the wires. And for the coding part, okay, it will be given in other professors' course. Of course, I told this before, and I don't want to do it again because I'm only paid to teach 3 courses every semester. Okay, if you want me to teach the course, fine, pay me more. All right, and this is very easy understanding figures from the basic idea, goes to design and fabrication, testing, and your product, just like we said before. All right, and there are 3 design alternatives. So in this course, we teach for custom design. That means you have to do everything on your own or with your teammates. Okay, you got to draw the line, draw the transistors, tune the size. Okay, and the coding, Verilog or VHDL will be taught in other courses, not this one. So if you don't have the background of language, fine. Okay, fine, that's fine. Okay, but you got to understand the basic electronics, which I believe that you already learned when you are a sophomore. And the second one is a cell-based design. That is the one I talk about, where you use the language, Verilog, to do the coding and then synthesis and do the PNR. Number 3 is that you don't have to bother go to the TSRI. It's called the FPGA-based design. You go to the shop store, you buy the FPGA board, download the software from the internet, then you can realize your idea on silicon just like that. Okay, and this is very good for prototyping, but it is not a real chip design. Okay, it is like an emulation. So there are three design alternatives. In this course, we only cover number 1. Okay. All right, and SPW and the MATLAB will not be covered. This is for the system level design. In this course, it was impossible because we only have like 16, maybe 15 weeks. So it's impossible to to teach you how to use these tools. But if you go to the system level design, you're going to need them. All right, and this is for the coding part. If you write a code like this, and it goes through a simulator, stand in the test bench, you see the functionality, where to check whether it's correct or not. This is for the code level, the code design. We will not cover. And then if you do develop the code, then you can synthesize the code into the hardware. And then you rerun the simulation again. Okay, we stop here. This is the thing that the students will learn, and you should learn in this course. This is called the virtuoso. It's a cadence tool. And here, you have a big window. Then the TAs will teach you how to call the transistor and tune the size, and then do the connections on the wiring between the transistors to make it work. And of course, you got an input pin and output pin, this kind of thing. Then after you finish the design in this graphic window, you can dump it into the SPICE code. So you don't have to write a SPICE code by yourself. You are lucky ones. 30 years ago, when I took the VLSI course in American, okay, we don't have the graphic tool. We have to write the SPICE code, okay, word by word, bit by bit, okay, and then go through the simulation. Okay, you can consider that a Stone Age. Right now, you are a civilized age. Or that was a Stone Age. We use the stick and the stone to fight for each other. Right now, you have what? You have the Gatling machine gun. You can shoot everything down. All right, and then after your design, you got to do the floor plan, placement, and the routing. But it'll be easy. Don't worry about it. I will guide you through to show you how to do it. Okay, and this is the layout. This is the second tough part. This is the layout of the design. For example, this is the inverter. You got to understand how to draw the layout of a transistor. Then you got to understand how to draw the layout of the entire systems and the buses that you need, and how to connect with the external world. Okay, how to deal with those buffers, drivers, and pads. Okay, these are required. So this is something that the foundry, TSMC, and UMC will understand. They will tape out the chip for you. It's called the layout. This is the second thing you will learn in this course. The number one is the schematic design. Number two is the layout design. Then after layout design, you have to run the simulation again, because after the layout is done, a lot of parasitic components will show up. For example, those things that we don't like. Parasitic capacitors, resistors, and the coil, and the inductance. Okay, we got to take those factors into consideration and rerun, and to see how it works again. Then after the post-layout simulation, and you find out that it is as good as the pre-layout simulation, then congratulations, you got a design so successful that we can send it to TSMC. Okay, and it's called a TTS2 file. And this file is a public standard, industrial standard that all the foundries understand. They can take it, and then they can take it and receive the bills, okay, and they can tape out for you. All right? But right now, for the educational chip, it's free. So you don't have to pay for that. And if you go to the graduate school to do the IC design, then your advisor will have to pay the bill. All right, and this is the measurement. After the chip was back, then you got to use a lot of equipment. For example, the logic analyzers, function generators, spectrum analyzers, network analyzers, these kind of things to do the measurement, to see how the chip works. All right, and they are very expensive. You got to use the tools. And for example, my lab will provide some of these tools. If you really need high-end stuff, for example, your chip, you claim your chip can run up to like 100 gigahertz. Sorry, we don't have that kind of thing. You can ask your advisor to pay the bill. You can rent the equipment from TSI. They have a lab which has a lot of this kind of high-end stuff over there. Anyway, so this is, right now, this is a beginner. You don't have to bother. And this is what you are supposed to see on the screen of the scope. Okay, you will see a lot of waves. Okay, hopefully, after your chip comes back, okay, you won't see a flat line. Okay, or the ground, or the VDD. All right, that's so pathetic. If you what happened to your design looks like last way, that basically you spend the whole semester to design a resistor. Damn, I spent the entire semester and the design. What design is a resistor? Why bother? Okay, at least you can see something like this. Okay, the inverters. Okay, high in, low out, low in, high out. Okay, or you can design an adder. Okay, adder to carry out the additions. 1 plus 1 is 2. Okay, you can then go home and tell your grandma. Okay, grandma, I finished the design of an adder. Okay, using a chip, my chip. I still have my chip in my drawer, my first chip. Okay, which was taped out 40 years ago. All right, in this course, we are going to cover digital designs. There is no analog. We don't have time for that. All right, only digital designs for the beginners to understand. All right, and then we'll talk about how to design the gates. We have, in the first year, it is my assumption that you took the digital system design. So I assume you understand what the logic gate is, but you perhaps you don't know what is the relationship between the gate and the transistors. So the devices, then we have to talk about the logic gates. Then it is pretty much the same as the first year course, digital IC design. We have to talk about a combinational logic networks, but this time we are going to go down to transistor level, not just gate level. Okay, all the way down to the transistor level. Then we'll talk about the sequential machine, okay, finite state machine, and subsystems. Then we talk about how to do the floor planning, all right, how to make some arrangement so that everything can be included in that small area, and then architecture design. If we do have some time, we'll talk about the EDA algorithms, which I don't think so. Because right now, the number of weeks we have in a single semester has been reduced from 18 to 16, including the midterm exams and the final exam. I don't know whose stupid idea is this, okay? Well, that'll save me a lot of pain anyway. All right, so students care. The second thing that, how to pass this course. So you need to finish a subsystem design. That's what I say, okay? Because we have a very short semesters. It's impossible for you to finish a CPU design. Come on, give me a break. If you can finish the CPU design, let me know, okay? I'll find some adventure VC to help you to establish a company. It's impossible, okay? I've been teaching this for 30 years, and no one has ever done that. So anyway, 8-bit adder is the lowest threshold for the team, for the student team to finish. Okay, anything lower than this one will not be acceptable. Okay, basically you can select the topics, design topic like 8-bit adders. There are a lot of adders. COA, CRCA, CSA, this kind of thing. Or you can use you can design multipliers, dividers. Okay, these are very fundamental arithmetic logic circuits. And of course, you're welcome to design memory. Okay, I really hope that some students can become memory tycoon to kick some ass in Korea, all right? And then you gotta find your teammates, because TSI will not allow every student to tape out on the chip. They hope that 2 or 3 students can be a team, you tape out the chip together. So you, if you are still interested in this course after the lecture, you can find your friends, okay, to work together. Right? What do you want to develop? Okay, don't be shy. This is a very good timing for you to get to know your friends in your class, because you never know someday these guys could be your colleagues, could be your helping hand when you are in the industry. And then the final exams or midterm, you should take it. Okay, there will be a written exam, and the overall credit will be given if your score is higher than 60. For the TSI, they support college students to tape out chips. There are 2 types. The first one is called the educational chip, which is the one that we are going to help you do that. Is the first one because it's free, and it's full custom. But the area and the pin count is limited. Pin count, I remember the number is 40. So the maximum number you can use is 40 pins. That's all, including the power and the ground. And the area is restricted to 1 by 1 or 1.2 by 1.2. You gotta ask your TAs, micrometer, okay? But in the future, you wanna be a master student, right? Okay. You wanna go to graduate school? Please raise your hand to get your master's degree. Raise your hand. Come on. You don't want to? You just want to get out of here with your bachelor's degree? It will not be competitive enough in the industry. Come on. So be real. All right. So if you go on and become a master student in this area, you're going to develop the advanced chip design. No limit of pin count, low limitation of area as well. But the thing is, the design must be evaluated by a committee. Then your professor will pay for partial of the overall cost. That's the big money. So you gotta find a rich professor to follow if you want to do the IC design research in the future. Okay, a professor with a very, very deep pocket. Okay, and there is no textbook. We just tell you a reference book. Professor Lin wrote a book in 2012. It's a very good one. I'm not sure that he has a new edition or not. You can check it out. That's his name. Okay, this book is very, very good. But even though that's 10 years of book, I still consider this is a very good one. Okay, it's your decision to buy it or not. Okay. And most of the time, I use my own PPT. Don't ask me to share the PowerPoint file, okay? If I need to take pictures, if you don't, that's fine, okay? Because this is my copyright. Well, the thing is, I remember a couple of years when I shared with PPT with the students, not only they distributed over the internet, and after they got the PPT, they never came to the class. But all right. And the main goal of this course is that I'd like to push the student to tape out a chip in the end of this semester. All right. This is the only way I know for students to learn the chip design from the top to the bottom. It's the only way I know. Okay. Become a soldier, become a warrior. You have to go to the battlefield. Okay. You will not become a real soldier, just play the video games. Come on. Video games is not equivalent to the real battlefield, right? All right, a team leader is needed. Why? Because the chip will be back after 3 months of this course. So somebody got in charge of the measurement. So I need someone in your team who will be alive, okay, in the next semester. I don't care about it's a girl or a boy, okay? He or she must be alive in next semester. And the deadline of the submission of this project is Friday, okay, 12 o'clock of the semester's final week, all right? And we are going to give you homeworks every week, okay? And homework credit is counted. So this is how the scores will be distributed. Okay, midterm, final will be 30 points each. Homework will be 20. The final project will be 20. Well, according to my experience, students, basically, most of them will fail in the exams. This is I don't know whether this is a tradition of the NSYSUWE, okay? So it's better for you to start working on a chip design if you're serious about this thing. Oh, by the way, there is another requirement I need help from you. Okay, please do not eat your breakfast in my course. All right? And of course, I'm asking not to eat your breakfast, but you gotta finish your breakfast before you get into my classroom. Is that understood? All right? I don't want to be hungry, but I cannot make you to let me feel I'm hungry. Okay, if you eat a very delicious food, it smells so good, okay, I cannot stand that because I will feel hungry. All right, I think that's about it. And then your TAs can be reached in the extension of 4149. That's that's the in-house phone number, and they will download. They will show you how to download the forecast design notes. Okay, this is a manual that we developed by our own lab, so it's free for you to download, no charge. Okay, trust me, you don't want to go through all the manuals. This is a very nice manual developed by our lab. And then if you were already understand how to use the Unix or Linux-based systems commands, that's fine. And if you are so addicted to the Windows-based system, then it's time for you to get to know this new system, Unix-based, because you got to type a lot of command line, not just draw the icons or this kind of thing. And of course, you can do your best or try your best to get the free spice simulator in your computer. That's fine. Okay, but I'll pretend I don't know nothing about this part, because sometimes it helps. You can do the simulation in your home. And then TA will give their recitation lectures, okay, in one of the evenings every week. And they are very good in the tool usage. It's better for you to go to their lectures. Otherwise, you'll have a big trouble if you want to do the design. All right, the last thing is that if you want to really take the course, think about it, because you're going to have a hard time, okay, particularly in the end of a semester. Okay, because at the end of the semester, you have a lot of courses to take the final exam, and it seems that you don't have time for this course. You got to think about it. All right, that's about everything I want to say here. So it's about 10:25. So any questions? Otherwise, I'm going to my Super Bowl second half. I think it's over. Damn. You boys make me lose my second half. I'm betting on Eagles. All right. Yeah, you can take photos. That's fine. Okay, the videotape IP belongs to the department. We do recording, and you can the video tape, the video of this course, okay, will be distributed inside the IP region of the W department. You cannot watch the videos from the outside, but the video will be available to all the IPs in the W department. Is that understood? You can sitting in the PC lab and watch the video. And I don't know the video address. You can ask the TAs or ask Miss Lee. Miss Lee in the WE office. You can take the photos in the class, that's fine, even though I don't look good, okay? And then the video is available to every students. All you need to know is to contact Miss Lee in the department office. Okay, she will tell you how to access it. All right? Anything else? I see a lot of blank faces, or you have to think about it. That's fine. All right, wish you have a nice day, and I'll see you next week. All right? Thank you, TAs. That's about it.